Now, what I want to call your attention to is that if we look at the reverse reaction, we see something a little different. So both of these reactions, as shown here, are equilibria, because what we're looking at are weak acids, things that dissociate a little bit, and once they do, are capable of going in either direction. In other words, once I make some of this methyl ammonium cation, it is capable of losing an H plus to become methylamine again. Same deal here. The moment I make acetic acid into acetate, that acetate ion is capable of picking up an H plus. Now, if I think about this in terms of the Bronsted-Lowry definition, if I think about the backwards reaction here, I think about this guy right here, methyl ammonium, throwing off a cation, or potentially taking that cation, that H plus, and putting it onto a water molecule. Well, what I would be tempted to call methyl ammonium is an acid, right? It's acting like an acid. When the reverse reaction takes place, it is now a proton donor. And by the same token, I would call acetate over here, if I'm going in reverse, in this case, looking at that reaction, what I see is acetate picking up an H plus, and therefore that would be acetate acting as a base. Well, the words we're going to have for these kinds of acids and bases, the ones we make from other identifiable things, is we refer to them as the conjugate acid, or the conjugate base of the thing that we made them from. And so if I want to find the conjugate pairs up here, what they are, conjugate pairs are always two species different by a single H plus. I guarantee you of that. You can say this in more elaborate, flowery ways. You can say that a conjugate base is what you get after an acid loses its proton, or that a conjugate acid is what you get after a base picks up a proton. But either way, what it specifically is just a pair of species that are different by one H plus. So if I look at our reactions up here, what I would have is, first off, as a pair, CH3 NH2 and CH3 NH3 plus. And in this case, that one's the acid, that one's the base. I could do the same thing with the acetate. CH3COOH and CH3COO minus. Again, acid, base, conjugate pair. Now there's another couple of conjugate pairs here that you might not pick up immediately if your focus is entirely on the things that contain carbon. And when we're doing biochemistry, you can be excused for that. But the other thing that we'll find that is acting as a conjugate pair is the thing that is receiving or giving off the protons to these guys, namely water is getting involved. And in fact, if I look at water and over here hydroxide, that is a conjugate pair. And in this case, water is acting as the acid, hydroxide as the base. Now I know that is going to be a weird thing to hear, the idea that water could be an acid. Don't worry, it is the weakest one you can possibly imagine, to the point that we don't really notice it doing much. But it is, in this case, losing a proton to the base, so it must be the acid. This might remind you a little bit of the oxidation reduction idea, where if one of those two things happens, the other one has to be happening as well. If I look over at this reaction, you'll notice you also get a situation where water and hydronium are a conjugate pair. Again, two species different by one H plus. In this case, water's the base because it's the thing receiving an H plus from the acetic acid. Hydronium in this case is your acid, but this would be a conjugate pair and that would be a conjugate pair. We can find these pretty much anywhere we see acid-base chemistry. And if there's one thing that I want to make sure you're incredibly clear on as we start doing this chemistry, because I know that the challenge of the last unit was trying to get used to the mechanics of running a particular chemical reaction. How do I add something across a double bond? How do I combine two molecules and remove H and OH? How do I get these things? Well, let me make it very clear. Acid-base chemistry is much simpler than you want it to be most of the time. Or maybe I should say much simpler than you expect it to be. You want it to be this simple. Trust me on that. what you're going to observe is that every acid-base reaction involves two things starting out, an acid and a base, and them each becoming their opposing conjugate. So the acid loses a proton, becomes its conjugate base. The base gains a proton, becomes its conjugate acid. That is all you'll ever see for acid-base reactions. And we're going to look at a few examples of that with amino acids in our next video.